Hello. We've already talked about exponential growth, so now we want to compare it to what we call continuous exponential growth. So if you ever see the word continuous, then it grows a little bit differently because it has a different base. So if you think back to what you know from college algebra, we talked about some compound interest formulas, and the first one was just compound interest, where n was the number of times it was compounded. So in our previous video, we talked about n being 1. So we were looking at something very basic where we start out with our initial amount principal and 1 plus the interest rate as a decimal, and then to the t power. So our base for our exponential growth came from that 1 plus r, and we called that base A. All right. We also talked about continuous compound interest, and we said here now, when it's continuous, that our base is E, which, remember, E is an irrational number. It's approximately 2.718. Okay, so we are comparing a base of A to a base of E. So let's take a look at how that affects our growth. If you remember, if compound interest was compounded continuously, it was compounded infinitely many times. So you did earn more money, and the bigger the amount in your account got, the faster it grew. Okay, and we are going to be talking not only about growth, but decay as well in the same situation. So our exponential growth function that we talked about previously, we said that base is A, and A is 1 plus the interest rate is a decimal, or the growth rate is a decimal. And remember, if it's growth, then A ends up being a number bigger than 1 because you're adding on. And if it's between 0 and 1, that is decay, it's decreasing at a certain rate. So let's talk about our continuous then. Our base is E, and they just switch in this book, which you also did in exponential growth and decay in college algebra, using K rather than R, but it's the same idea. It's a percent as a decimal. If K is positive, it's growth. If K is negative, it's decay. All right, so let's look at an example and compare the two. So if I start out with 1,000 bunnies, okay, the population of bunnies grows at a rate of 4% per year. Okay, so we need to find our base A, which is 1 plus, well, let's say it this way first. So it's 100% plus 4%. So if you think about that, then we need the decimal equivalents. So 100% is 1, 4% as a decimal is 0.04. So my base for my growth function is going to be 1.04. Okay, so if I write that, then I have P equals my initial population, which is 1,000, times 1.04 to the t power. Okay. All right, that's my first population, so I'm just going to call it, P sub 1. Okay, so my second population, or the same population, what happens if it grows continuously? That's when we know we need to use our base of E. So we have a base of E, and it says it's growing at a rate of 4% per year. So that is our growth rate, K, and we would use that as a decimal equivalent for that percent. Okay, so my continuous exponential growth function for the population of bunnies, I'll call it P sub 2, would be 1,000 times base E to the 0.04 to the t power. So 0.04 is positive because it is growth. Okay, so if we want to look at those graphically, one thing we can think about is why is the continuous growing faster? Well, if we think about it, I can look at this as e to the 0.04 is my base. Okay, it's like 1.04 here is my base. Well, this is my base here. If we put that into a calculator, that becomes e to the 0.04 power becomes 1.0408, etc. Okay, so it's like I have an exponential growth function with a base of 1.0408 rather than 1.04. So it is slightly larger. Okay, so that's 1,000. Fix this a little bit. There we go. Okay, so if I look at the graph of these two, we're talking about our independent variable being time and the population, P. So both start at 1,000. That's my vertical intercept, the initial amount. And P sub 1 will grow slightly slower. Ever so slightly. My picture's a little bit out of scale because of what I've got going on here, but this one will grow a little bit faster because the base is a little bit larger. Okay, so let's talk about how do we convert between a base of A, an exponential function that has base A versus base E. So growth, if it's continuous or not continuous. Okay, so let's look at an example here. Okay, so it says find the annual percent growth rate that is equivalent to a continuous percent growth rate of 8%. Okay, so if we know the continuous percent growth rate, then we can come up with our function that calculates that continuous growth. Okay, so if it's a growth rate of 8%, that is my K as a decimal. Okay, so what I need to do is just like I did in the last example, so this is very similar, is whatever our initial amount is, P sub 0, okay, we need to convert e to the 0.08. We need to convert this base to some number a, which is a number between, well, actually it should be greater than 1 because it is growth, okay? Or we need to figure out what is that rate. Remember, a is 1 plus r. So we are looking for, if we're looking for the growth rate, we're looking for r. So if we can come up with a, then we can get r from that. All right, so all we have to do is put this in our calculator. What is the calculator equivalent of that? And if we do that, that comes out to be 1.08328, etc. So as we expect, it's going to be a little bit larger, the 8%, a little bit larger than 8%. Okay, so this is telling me basically that this is 1 plus 0.08328, which this is my growth rate as a decimal, so I convert that to a percent, which becomes 8.3. And if we want, we could round it to 3, depends on what rounding we want. So if we have a continuous growth rate of 8%, then we have to have an annual growth rate of 8.33%. So it has to be bigger at the annual to get the same amount of money it would get at a continuous rate of 8%. Okay, so let's go the other direction. Now, this one's a little bit trickier because it requires us to know some stuff about logarithms and exponential functions. So let's do a quick review of that on the side. Okay, so if you recall, y equals e to the x and y equals the natural log of x are inverse functions. And you learned in college algebra some properties of inverse functions, which basically there was one that said if you had the natural log of e to some power, that gives you that power. Because it's basically one is undoing the other. It's the inverse property. So if I say, sorry, and then there's another one. So if we say e, so it's the other way around, e to the natural log of some number will be equal to that number. Okay, so this is, these properties are what we are going to use to come up with our continuous percent growth rate. So, for example, our situation here is we need to rewrite 1.13 as e to a power. Okay, and this is how we do it. Okay, because if I say e to the natural log of some number, I get that number back. Well, my number is 1.3. So I will rewrite that 1.13 using those properties, and I'm going to rewrite that as e to the natural log of 1.13. So if you put that in your calculator, if you put e to the natural log of 1.13 in your calculator, you should get 1.13 back. They are inverses. Raising something to a power and then taking the natural log, one undoes the other. Okay? So then all we have to do is convert that, oops, I forgot my T. Now all we have to do is convert this to a decimal, and that will tell us our growth rate. So then it's just calculator work again. So I have e to the, let me write this color here, 0.1222 dot 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 power to the t. All right, so basically natural log excuse me, of 1.13 is this decimal. And now we know that this number, that's the exponent on e, tells us the decimal equivalent of our exponential, or our continuous exponential growth rate. And all kinds of problems here. Tablets. Low. So we could say that this is e to the 0.1222 t power, which then tells me that What is this as a percent? It tells me that my continuous percent growth rate is 12.22%. So this one's a little trickier. So give some of those practice problems in your homework a try and see how it goes.